Hello everybody and welcome back. So we have seen some connections between data types and category theory, but let's drill down deeper. So we have previously seen that if we have a data type which comes with a functor, then we can construct this category of algebras for this functor, where the objects are sets X together with something we think of as constructors for this data type, and the morphisms are these structure preserving morphisms between the underlying things. And we saw that for the case of the natural numbers, then being structure preserving meant exactly that we are sending 0 to 0 and successor to successor, right? So it makes sense to think that to have a data type means to have such an algebra such that we have pattern matching, that is, that we have such a morphism to every other algebra, right? If we can give right-hand sides here, then we should be able to define this function by pattern matching. So this concept is the concept of an initial algebra. So it's initial because it's the first one with morphisms to all the other ones, right? And the formal definition is as follows. So let's work through it slowly. So we have some algebra x and con. So that means that we have here f of x and con, which we think of as our constructors, goes into x. And now the claim is that this is initial. And that means that the following holds, that if we have any other algebra y, so we have y here, we have f of y, and we have some way of interpreting all the structure with an f. So for every such y and f, there should exist a unique morphism from x to y, which is usually called fold f. And it should be an algebra morphism, so that means that this diagram should commute, right? But here I can do f of fold f. So that means that this morphism here is exactly structure preserving. So it's going to send 0 to the 0, this algebra, etc. So we get this by something that looks like pattern matching, right? So let's see if we can do this in Agda. So let's just do it for the natural numbers for now. So here I've specialized all our generic machinery to the natural numbers. I have the functor for natural numbers. I have the constructor. I have the functorial action, the f map, and I have proof that this has identities, preserves identities in composition. Right. Now I would like to define this fold, which, given any other algebra A with an f, takes me from the natural numbers to A. Right. Okay, so how would I do that? Well, as always, we do it by pattern matching, because pattern matching is what we're trying to capture here, right? So I can pattern match on n, but it's going to give me all of these artifacts of the encoding, so I'm just going to do this myself. I have a successor, and I have a 0. Everything has a prime on it because this was the second encoding that we used. But it doesn't matter. Okay, so what should we do here for 0? Well, we should send this 0 to whatever f tells us to send it to, right? F is the only way we have of constructing something in A. So here I have to do f of something. Okay, and then we see here again that now we just have to construct something in our good old args functor for the natural numbers, which was defined to be like this, right? So we have a boolean, which tells us if we should choose 0 or successor. And in this case, I want to choose the 0 of A, so that corresponds to true. And then here I have to give the rest of the arguments, which for 0 is nothing, right? So TT. And for the successor, I should again use F. Now I want the successor case, so that will be represented by false. And then here I have to give one more argument, which I get by a recursive call as before. So we used a lot of fancy words to describe this, but to define it, it's just pattern matching that we've done from almost on day one, right? So that gives us the fold. But then we also should check that this diagram commutes. So save that for later. So remember that the claim was that if I first go here and then down, that should be the same as going down and across. That's what it means to be an algebra morphism, right? So let's see if that's true. So that's this. So here I'm first going across with the constructor, and then I'm going down on the right. And here I'm first going down with the functor applied to the thing, and then here I'm going across with the other algebra, right? And as usual, because here I'm proving an equation between functions, I better do this with function extensionality, and I better do this by pattern matching on X. Right. Okay, and then I see that I have basically two choices. Either I'm in the 0 case, which is represented by true and something. I know that this is TT, in fact. Or I'm in the successor case, which is represented by false, and here a recursive call. Right. Let's look at the 0 case. Well, that was easy. And let's look at the successor case. Well, that was also easy. So we see that by the way we define this thing, this is almost true by definition, right? We just have to look at these two cases because here we're doing the same pattern matching. So the fact that the diagram commutes is almost immediately captured by the pattern matching. And to show that it's unique is a little bit more difficult, but not completely so. So the uniqueness just is something we need later for doing dependent pattern matching. So without uniqueness, we could still do this. But okay, so what does it say? It says that if I have any other H, which looks like the fold, right, such that the diagram commutes, then H equals the fold. And I've proven this. This is meant to be used with extensionality, so we prove it for every n, right, for convenience. And we pattern match on the end, we have these two cases. Let's look at the first one. What do we have to prove? Well, it's a little bit hard to read, but we have to prove that H of 0 is equal to 0 in A. Right. Let's see what P says. P is our proof of this equation. What does P say if we apply it to true in TT? So P is just an equation between functions, so we can't apply it directly, but we had this Kong app, which is just Kong of app, which says that if two functions are equal and you apply them to the same thing, then the result is equal. Right? So it's the inverse of function extensionality. Right? So if I do Kong app of P and I apply this to true TT, in the space, and I normalize this, then I see that that says exactly that they are the same at 0. Okay, and what about the successor case? Well, let's try the same thing, right? Maybe it just works. Have to use the P after all. So here we are in the successor case, so we have a false and some recursive call. Okay, so we see that the start looks good, but we don't get all the way to where we want to be. Right, so let's do this with a trans. Step 1, I'm too lazy to set up a equational reasoning thing. But I think there's going to be many steps anyway. Okay, so now I need this to hold. Well, it looks like most of it is okay. Let's do a Kong on the pieces that are okay. Okay, I think this is what's left. And this exactly looks like a recursive call, right? So we could prove that again using pattern matching. So we realized that pattern matching gets us everything we want here. And let's quickly just do the same thing for arbitrary data types. So here I have prepared some of it already for an arbitrary described data type, and the story is pretty much the same as before. I want to define the fold, but I have to do it together mutually with a special case of the args functor. So let's see if I can define it. If I have a constructor, then I want an A. The only way I can get an A is if I use F. And then here I want an args of A, and I have an args of something else. So I have to use the specialized args fold. D and F and X, and that gets me there. Right. So again, all the work is being done by this, which is doing pattern matching on the code. And then here I've proven that in fact args fold is a special case of args map, where the function is fold, because this is what you need to show the equation. So here is the same thing again, that the diagram commutes. If I first go across and then go down, it should be the same thing as first going down and then going across. And of course, we prove this with function extensionality. Okay. And here we get an X. Like this. Okay, and then it looks like some things have already started to reduce because we're actually applying these things to the constructor, right? The F's are the same on both sides. We can do a con F. And then here we need exactly that args fold is the same of an args map over fold. That's why we prepared that thing. D first. Okay. And for uniqueness, we again have do pattern matching on the X, I think. Is that right? No. Okay, let's see. So we have this equation. We know that H is an algebra morphism. So that thing here looks like the good beginning of this. So let's do another trans. Let's see what we have first. So we have H, we have P. And if we do a con up of P, apply to X, that's a good start. So let's do that with a trans. And then do a con F something. And this looks like this other specialization of the previous proof. So this takes a D and an H, and a P and X. Right. So all the heavy lifting is again done by just checking that the args map is the same as the args fold, and we are otherwise getting almost all the way there just by knowing that H is an algebra map. Right. So to zoom out a little bit to see what we've actually done, maybe it's easy to just look at the natural number example. We see that using pattern matching, we get that the natural number is an initial algebra. So for every other algebra, we get a map to it such that a certain diagram commutes, and this map is unique. So this is the only map that satisfies this. If any other map does it, then it's equal to this one. So that's a way to describe what is going on with pattern matching in categorical terms.